There we go. All right, so we're gonna implement what we learned last time into actual code, and we're gonna use that in order to predict handwritten digits. And the data set that we're gonna use is a common data set. It's called MNIST, and we're gonna use a neural network to try to predict which, given an image, which what label is it? Is it a 0 or is it a 1 all the way to 9? And so this is it's a Google Colab notebook. And this makes editing, running, and programming with Python, and especially with neural networks, pretty easy. So I'm going to share the link to you guys, and I recommend copying this and running this yourself, playing around with it, and experimenting with this as we go through each line of code. All right, so the main thing that we're gonna go through the code of implementing a neural network and applying it to a data set. But if you guys get caught up on some line of code, some function that you don't understand, don't worry about it. It's not too important to understand a line of code or this or that. What you guys should understand is that most of these have been come up by experimentation. And that's the big factor of actually applying neural networks is many times in the real world, you're gonna have a data set where it's not perfect and you don't know how many neurons you have to use, how many layers you have to use. And what you have to do is experiment with it, try different configurations and try different techniques. And you're trying to increase the accuracy. And so just, if you don't understand the piece of code, don't worry about it, but try to learn the techniques, the general techniques that I'm going to be talking about today, because this is what the main goal of this lecture will be. And so we're going to this is how you run, by the way, notebook. You press this play button, or this, yeah. And so this is going to run the first line. And so just the first line, this is a matplotlib. This is a Python library for graphical analysis. You can use plots, you can graphs, images, and we're going to just use this to look at images. All right, so next we're going to talk about NumPy and the basics of NumPy. So NumPy is a library built for Python. It provides it makes it easy to manipulate multi-dimensional arrays and matrices. And this is used in machine learning and data science because the data that we get is arrays. It's a bunch of matrices. And so we need to manipulate these in order to feed that into our network. And so the first thing we do is import. This is how we import a library. We just do import NumPy. As NP is just, this is what we're going to call our NumPy library in the future. And so when we want to create an array, we first assign it to some variable, and we do NumPy np.array is equal to some list. If you guys are familiar with Python, you'll know that this is just a list. If you guys are familiar with R, in R you just do the C parentheses and the number of elements in that list. And so this is similar to making a vector or a list. And so this is gonna make it into a NumPy array. And so this allows us to easily manipulate and easily do efficient data structures on our data. And this is important because we sometimes have millions of data points. And so if we just want to add or subtract something, well, if we have a bad implementation, then it's going to take a long time. And so we need an efficient manipulation of this. And so again, we run this by pressing this play button. And so we print out our array, and as expected, we get our list, which is a 1, 2, and 3. And this 1, 2, and 3 is what we defined here as our list. We can also print out the shape of this array, and we can see that this is a 3, comma, nothing. So what this means is that it's a one-dimensional array, and there's 3 elements inside of that array. All right, now let's say we want to create a 2-dimensional array. We set NumPy, it's the same thing, NumPy.array, But a two-dimensional array is an array inside of an array. And so we're going to have this first array, comma, our second array. And that's encompassed all into a single array. So it's an array inside of an array. And when we print that, we also get 1, 2, 3, and 4, 5, 6. And as you can see, this is an array inside of the array. And when we print the shape of that array, we just do the array variable dot shape. We get a 2 by 3. This 2 is the number of arrays that we have. As you can see, we have one array, and then we have another array. So that's 2 arrays. And the 3 is the number of elements inside of that array. So we have 1, 2, 3. We have 3 elements. And you can have as many dimensions as needed. So you can have a 3-dimensional array or a 4-dimensional array. And so there's many more functions for NumPy. You can add different things, and we'll talk about that later. But it all depends on what we're trying to do, our task. And we'll use some of these functions when we try to predict handwritten digits. So next, we're going to talk about TensorFlow. And this is an open source library provided by Google. It makes implementing and training neural networks very easy. So every time we wanted to go train some network, we don't want to keep making the same, we don't want to keep programming things. So TensorFlow does this for us, and it makes experimenting, it makes doing different variations very fast. And so TensorFlow is built for manipulating tensors. For example, NumPy was to manipulate arrays. Tensors are kind of pretty much arrays, but you can have, it's a different kind of array. And TensorFlow is kind of built on top of that. And so we're first going to import TensorFlow as TF. And again, this is just a call TensorFlow. And it might take a little bit because it's a kind of heavy library. But then, okay, this is how we create tensors. And think of tensors just as arrays. But we have some number, and we're going to assign that to tf.constant. Now we're going to assign that constant to some float value. Now this isn't really an array, right? This is a constant. But you can think of this as an array of rank 0. What that means is that it's a 0-dimensional array. And so it has no dimensions, which means it's just a constant value. And when we actually print this out, we can see that we get tf.tensor, this is our TensorFlow class, and we get the value with the shape of, there's no shape. It's just a 0 rank tensor, and there's nothing in it except that constant value. And when we print out the rank of that tensor, we get a rank of 0. Again, because this is a 0-dimensional array. Now, if we want to make a 1-dimensional array or a 1-dimensional tensor, we again do tf.constant, and this is the same way as the NumPy. We just do it as a list of values. And then when we print that out, we see that we have a tf of tensor of the list that we declared with a shape of 2. And this shape, again, is the number of elements in this array. And this, you guys can see, this is a rank of 1, which means it's a 1-dimensional array. And finally, TensorFlow is also compatible with NumPy. And so we can actually initialize the NumPy array like we did in the previous grid. And we can actually feed that into our tf.constant with our NumPy array. And we print that out again, we get exactly the same thing as we did as right here. And so we can, again, also create 2-dimensional tensor. And that's just an array inside of an array. And we get the same thing with the shape being 2 by 4. And we get a rank 2 tensor. So we also have math operations in TensorFlow. We can add, subtract, multiply. If you guys are familiar with linear algebra, we can dot product, we can matrix multiply. It's not too important if you don't know it, but we can do different operations, and these are efficient operations. And so we first define a tf.constant of some integer, of 5 and of 2. And then when we run this, we can add. The way we add is tf.add a and b, and we see we get 7. We can also subtract, we get 3, 5 minus 2. Also multiply 5 times 2 and then divide, 5 divided by 2. And so, yeah, you can also add different arrays. So in this example, we added and subtracted integer values. But we can do the same thing with arrays and arrays of different dimensions. So for example, a one-dimensional array, as we can see here, we can do this for more dimensions. When we run this, we see that when we add different arrays, we add the elements of that specific element. So we're at index 0, we're going to add 1, and we're going to have 4, and we're going to get our 5. And this does the same thing for subtract, multiply, and divide. And of course, we actually get a shape in this case. All right, so that's nice, but we want to connect this to neural networks. And so if you guys remember from the previous lecture, our neural network operation is we have some weights, we multiply it by our inputs, and we add a bias to it. We then add some sigmoid. We input that into some sigmoid function or some activation function. And so we're gonna actually implement this using TensorFlow. And again, it's not too important if you guys don't understand a line of code or anything, it doesn't really matter. But just understand the operations that are going into this. And this code is just a translation of this image that we see here. And so we're first going to define our function. And this is, we just do def function name. And we're going to have two inputs. The first input is our x. This is our data. Our second input is the number of outputs. So for example, if we want 3 outputs, we're going to specify that to be 3. And so let's actually skip the actual function and look at the data. And so we initialize the data is going to be equal to a tf.constant, a tensor of a one-dimensional array. This array has 7 elements in it. We also are going to specify 5 outputs. Let's say we have 5 classes and we want 5 different outputs. This can be as many as you want. Same with the data. We can have as many elements as we want in this data. So what we're gonna do is we need to initialize our weights randomly. Remember, starting off, our weights are just random. They're bad values. We learn our weights using gradient descent as we go on, but initially we don't have good weights. And so what we do in this line of code is we do tf.random.uniform. This just creates a random value of weights of the shape. Now this might be a little bit confusing, but this is the x.shape of -1. What this is doing is getting the shape of our data. Our data is this tf.constant. It's getting the shape of this. This is a one-dimensional array with 7 elements. So the shape of this index is the previous, it's the last index of the shape. Well, the last index of a one-dimensional array is just 7. So whenever it takes this right here, it's just going to be 7 for this specific data. And same with the num outputs. The num outputs we specify here to be 5. And so we're expecting a 7 by 5 array. And so our weights are going to be 7 by 5. Our bias, on the other hand, is going to be a 1 by 5. Why is it 1 by 5? Well, all right, let's look at our formula right here. Right here in our previous lecture. We have the summation of our weights times our bias, times our inputs plus our bias. Right. Well, if you guys are familiar with linear algebra, you'll know that in order to multiply the inputs, because our inputs is a shape of 7, right? We have a 7. We have 7 elements inside our data. And so we want to multiply that to our weights. Remember, we have our weights times our inputs. And the way we multiply that is we need a shape of 7 by 5. We have 5 because that's the number of outputs. But when we look into our z, this is our operation where and if you look at this image, this is the z is equal to our inputs times our weight plus our bias. And so we're gonna do a tf.matmul. If you're familiar with linear algebra, this is just a matrix multiplication. If you're not, it's not too important, but this is just multiplying our inputs by our weights. And then we're adding the bias to this. This is the same thing as doing tf.add. And so let's actually print this out. So first we're gonna print out the weights. What do our weights look like? Our weights are just random values. They're just random numbers with the shape of 7 by 5. Again, the 7 is from the number of elements in our data, and the 5 is from the number of outputs that we have. And as you guys can see, this is a 7 by 5 matrix with random values in it. Same with our bias, except our bias is going to be a 1 by 5 shape. And this is just with random values inside of it. And when we use gradient descent, we're going to actually learn what those values are. But right now, it's just randomly initialized. And so what we're going to do is multiply that into our z, or we're going to multiply those weights and our inputs plus the bias. And when we print out what that value is, we get this tensor. And so this, again, it's going to be kind of random because we have random weights. But we're going to multiply those weights by our inputs. And then we get a shape of 1 by 5. Again, if you're familiar with linear algebra, you'll know why this is so, because if you multiply a 7 by 5 times a 1 by 5, or times a 7, no, if you multiply a 7 by 1 times a 5 by 7 times a 7 by 1, you get a 1 by 5 matrix. And so this is what our z value is. And this is what we want, because if we see we have 5 elements inside this array, but we specify the number of outputs we want 5 outputs. And so we get exactly 5 outputs. And then we apply our activation. The way we apply the activation is by doing tf.sigmoid. Sigmoid is if we wanted to use our activation, but we could use ReLU, we could use tanh, and we would use Tensorflow for that. And what that does is it applies a sigmoid formula for each value in our prediction. And so this is going to be our actual prediction. Obviously, this is not a good prediction because it hasn't learned anything. Our weights are randomly initialized. But again, we get the expected output of a shape of 5 because we have 5 outputs, and that's how many shapes we wanted. And so I think there's a question about this last time, but what if we want more layers, right? This function is right now, this is only for 1 layer. If we want to add more layers, that's going to be our function inside of our function. Let me show it with this. We have our prediction, and that's going to be equal to our function. But instead of the inputs being our data, our input is going to be another function. And that function is going to have our data inputs. And for example, maybe our hidden layers, our first hidden layer is we want it to have 3 neurons. We specify to have the number of outputs to be 3. And same with, let's say we want our final output to have 5 neurons, we specify that to have 5. And when we print that, we see, when we go over here, we see that we get a shape, again, of 5. And so this is our prediction, but with 2 layers instead of 1. And so now we don't want to, when we're working with data, when we're trying to predict stuff, we don't want to keep making this function. And that's where TensorFlow comes in. And we first import the libraries that we want. So we do from TensorFlow.keras, import sequential. I explained this last time, but sequential is it just means a feed-forward neural network. So it just means 1 layer after the other. And then we're going to import our layers. And so we're going to import the dense layer. TensorFlow calls this dense. That just means a layer of our neural network. And this dropout I'll talk about later when we're actually implementing the handwritten digits. But let me just show you how we actually implement a model. So let's say, again, we want 5 outputs. What we do is we set model is going to be equal to our sequential And then we initialize some array with thence. We imported thence, right? With the number of outputs, and then we specify the activation that we want. If we want a sigmoid, we'll say sigmoid. If we want a relu, we'll say relu. And it all depends on our task, but the most common is usually relu. And there's different ways. I'm gonna tell you guys to not, if you guys see this like looking at code, other people's code, to not get confused because there's different ways of specifying the number of layers. So we could, the second way of doing that is model is equal to sequential, and then we do model.add, and then we're gonna add the dense layer of, again, 5 outputs with the activation of whichever activation we want. And again, if we wanna add more, then we'll do model2.add, and then the same thing. So we'll add as many layers as we want. And same thing, the way of doing this is a little confusing in my opinion, but just so you guys don't get confused, this is another way of doing it. Where we set our model equal to our sequential model, and then we set our layer equal to our model, and then the model is sort of a function. So that inside of that function is our dense layer. It's a little bit confusing doing it like that, but just so you guys don't get confused, that's another way of doing it. And so we run that and we initialize each model. And now we want to actually, how do we actually predict our data? Well, we're going to run data is equal to tf.constant. Remember, this is just initializing some array, some tensor. And then we're going to do print model, and we feed our data into our model. And so when we print it, we see we get a shape of 5. The 5 is from the number of outputs we wanted. And so again, this is a bad prediction because our weights were randomly initialized. And TensorFlow randomly initializes our weights for us. And so when we print out our prediction, this is a bad prediction. All right, so those are kind of the basics of TensorFlow. But we're gonna actually apply this to handwritten digits, to image recognition. And so this is a common data set used. It's called MNIST, and there's about 70,000 images of their handwritten images from 0 to 9. For example, someone sat down and they drew the number 6, and that's one image. And there's 70,000 of these. And these are of size 28 by 28. I'll explain what that means a little bit later. But first, what we want to import this data. So we do tensorflow.keras.datasets import MNIST. And then we call this function, which is provided by TensorFlow. Now, this is one difference from real world data. And this is something that we're not going to go over today, but it's an important thing to know. In the real world, you might get data that's bad. So what I mean by that is it's not processed correctly. There might be a bunch of missing data. There might be a bunch of values that are null. And it's your job to figure out which features, which data should I get rid of, what should I keep, and it's your job to process this data. This kind of comes with practice. It kind of comes with seeing a bunch of data. And there's really no way to teach this except just to go and do it. And we're not going to do that today. I'm just going to talk about the basic techniques of training a neural network and applying it to this data set. But this data set is pre-processed for us. There's no missing values. There's no null values. And so this makes it easy for us to just learn about it for now. But just know that in the real world, you might have a lot of messy data, and you might have to make some sacrifices, and you might have to drop some data that you might need because it's missing some data, and you have to make all these choices. And so in this data set, we load the data, and we set it equal to X train, Y train, X test, and Y test. Now what this is doing is assigning X train to be 60,000 of our images. And let me actually run this. And so it downloads the data. And then we print out the shape of our X train. When we look at Extreme, we have 60,000 images of size 28 by 28. Let me explain what this 28 by 28 is. 28 by 28 is the size of our image. So images represented in the computer are just pixel values. And so when we have a size of 28 by 28, that means we have pixel values of row 28 and of column 28. And that's how our computer understands that this is an image. And depending on the values in those pixels, that's what creates an image. And we want to use those pixel values into our neural network so that our neural network, given those pixel values, can learn from that data. And so why do we separate out our X train and X test? Why do we have two different variables for this? Why do we have a train and a test? Well, this is very good practice and common practice when training a neural network, because we want to evaluate our model. We want to see, did our model actually learn, or is it just overfitting? The way it overfits is by just memorizing the data that we give it. Well, so instead of just testing it on that memorized data, because on that memorized data, it's going to do pretty good, right? Because it's just memorizing data, it's overfitting. So what we do is we evaluate it to our X test. X test is data that it's never seen before. And that's the evaluation accuracy that we really care about, because that's what tells us if our model overfitted. For example, if our training accuracy is 90%, and then we get our testing accuracy to be 20%, we know that our model overfitted, and we need to create a better model. Do you guys have any questions?
I think it's good so far for me.
All right, so yeah, so we have our X train. Let's look at the shape of our data that we got. And again, our X train is going to be 60,000 images by 28 by 28. Our Y train, on the other hand, is just going to be 60,000 images, or not images, 60,000, and that's it. It's just of one value. And when we print, let's actually print out what does our Y train look like. And this is what our Y train is. It's 5, 0, 4, and there's 60,000 of these. Now, what is our Y train? Our Y train is our labeled data set. Remember, we're doing supervised learning, which means we have our data and we have our labeled data set. So this is what our labels are. It's our Y train. And let's say so this number 5, this is associated to the first image. This number 5 tells us that the first X train, we have 60,000 X trains. The first one is going to be a handwritten image of the number 5. And same with the Y train. With the X test, we're going to have 10,000 of these, of image 28 by 28, and 10,000 Y tests. And so when we actually print it out, this is matplotlib, by the way, and this actually prints out the image. We're going to see that the first image is the number 5, and the associated label is this 5. And so this image is our X, it's our data, and the 5 is our Y, it's our labeled data set. And again, when we print out the shape of our first image, we get 28 by 28, which just means that we have 28 pixels rows and 28 pixel columns. And so let me actually show you what pixel data looks like, what an image actually is. And so when we print out our X train, we get this really long array. And this is our 28 by 28 image data. And you guys can see there's a bunch of integers, there's a bunch of pixel values. And each integer is 1 pixel. And each pixel means something. For example, I believe these zeros represent black, and then 255 represents white. And all the images, all the pixels in between are some shade of color. So maybe 94 is some shade of red or something like that. And that's how our computer can know, that's how our computer can show us an image, because all the raw processing that goes on is just this two-dimensional array. And so this is what an image actually is. Now, actually, so that's not entirely true, because actual images, so when you take a picture with your camera, your camera image is actually an RGB image, which means it has actually actually a three-dimensional array. What we have in this data set is a two-dimensional array. Why it's not three-dimensional is because it's automatically converted from RGB into grayscale. And so what grayscale data does is it's just a gray image with no colors. And this is done for us. Of course, if you had your own images and you wanted to put that into a neural network, you would convert it into grayscale. And that's one technique that's used. Of course, though, let's say you have a task that you want to determine what the color of an image is, you wouldn't want to convert your images to grayscale, because you would lose all image information or all color information. But right now, we don't really care about color. And so what we do is it's automatically done for us, but it converts this RGB image into a grayscale image. And that's why we have a 28 by 28, a 2D array. And actually the reason why we also convert it to grayscale is it does help our neural network. So it does help with accuracy, and it does help with efficiency as well, because there's not as much data that our neural network has to learn from. So it takes a little bit less time. And then, so we haven't learned a technique though we have a two-dimensional array of images, 28 by 28, but we haven't learned any techniques to handle two-dimensional arrays, right? Our neural network, we've learned that it can only take in a one-dimensional array. And so what we need to do is actually convert this two-dimensional array into a one-dimensional array. And how we do that is using a NumPy function called flatten. And so we take this is just an example, we take our first image and we call dot flatten on it. And when we print out what is that shape, we get the shape of 784. As you guys can see, and when we print out that shape, this is the same data, but now it's a one-dimensional array. And so we can actually feed this into our neural network. Because if you guys try to feed in a two-dimensional array, you'll get an error, because it can't handle a one-dimensional array. At least the basic neural network can't. We'll learn about techniques to handle 2D arrays in different lectures, but right now we don't know about any techniques. And so we need to flatten our array. And so actually, an even faster way of doing this is if we reshape our array. This is a NumPy function, but what we do is we call reshape of 60,000. This 60,000 is the number of images we have in our X train, and we reshape that by 28 by 28. Why is it 28 by 28? Because that's our 784 value. For example, we multiply 28 by 28, we get 784. And that's the number of pixels that are in our image. And all we're doing is flattening that 2D array into a 1D array. And so we're getting a 28 by 28, 28 times 28, which is 784. And we do the same thing for our X test, but our X test only has 10,000 images. So that's one technique that we have to do. We're forced to do that. We have to make it into a 1D array. The next technique is scaling our data or normalizing our data. Neural networks, remember, they're just taking input data. Our input data in this case is just image data. It's this 0, it's this 136, this 253. And we want to help out our network because it could become very costly in some cases, right? the number of the more layers we have, the more neurons we have, the more our computer can't handle it. And so, or it might take longer to train. And so we want to help out our neural network by scaling this data. And this is one technique. It's not, you don't have to do it, but basically some people, I believe, they just experimented and they found that when you scale your data, you get a higher accuracy. And so we're going to scale our data, which means that we're going to, instead of feeding 133 or feeding 11 into our image, we're going to divide everything by 255. Why 255? Because we have the maximum value is 255, the maximum pixel value. And so when we actually divide everything by 255 and we print out our image, we can see this is our same image, but it's scaled. Instead of having 255, instead of having 31, we have integer, we have scaled numbers. And this number is going to be from 0 to 1. And it's 0 to 1 because we scale. The maximum is 255 and the minimum is 0. And so maybe this integer, this pixel value right here represents the color green. But now it's scaled. It's scaled down. And so this is going to actually help out our neural network to learn a little bit faster. And I actually encourage you guys, try not scaling it and see what accuracy do you guys get. Because the main thing you guys should get about this is experiment, try different things, because there really is no set way of doing something. And the set ways that are used today are just because they were experimented, they were just tried, and they found that the accuracy is higher in some cases. And so now let's actually build our model. Let's actually build our neural network. And so when we look at our task, what are we trying to do? We're trying to take an image and we're trying to predict what value that image is. Is it a 0? Is it a 9? Is it a 5? And we have, it's from 0 to 9. Well, what if we didn't know? And what if we didn't know this is a classification task? I'll tell you guys right now, this is a classification task. Why? Because a classification task is trying to predict categories. And we have categories in this case, right? Our category is it a 0? Is it a 1? Is it a 9? A regression task is some value, some constant value. So if it's for housing data, it might be predicting a $500,000 value. That's not a classification task, that's a regression task. But let's say for some reason, our task was hard and we just didn't know. We don't know if it's a regression task or a classification task. Well, let's try both of them. Let's just try using a regression in this case. And so we're gonna first set our model equal to our sequential model. And then we're gonna do model.add. Again, there's about 3 different ways of doing this, but I'm gonna use model.add. And then we're gonna set dense to the number of neurons. Now, I'm gonna set this to 64. This is kind of a random value I just set. For some reason, I'm not really sure why, but most neurons are set in powers of 16 or factors of 16. For example, maybe this is 16 or 32. And I believe this might be just because people experimented and they found out that powers of 16 or 32 work better. I'm not really sure, but this is kind of the customary way. But there's no really correct way of doing this. There's no correct way of finding the number of neurons. It just comes from experimentation. And same with the number of layers. If this task was just thrown to us, we don't really know the correct number of layers. And so it just comes from experimentation. And so I'm just gonna set it to 64. I highly encourage you guys to go back and set these to different values. Add more layers. So for example, right now there's 3 different layers, right? We have dense, dense, dense. We have 3 different denses. I highly encourage you guys, add more layers, add more neurons, take away neurons and see what happens. What happens to the accuracy? And so we also specify the activation. I'm gonna use ReLU. ReLU is fast, it's efficient, and it gets good accuracy. So Commonly, you'll just use ReLU in most cases. The second layer, I'm setting to 32. There's no really a reason why, but we'll see how accurate is this. And again, we'll set the activation to ReLU. Our last layer is important. It depends on our task. In this case, we're doing a regression task. We want one single value. We want to predict, is it a 5? And we want that regression task to be a 5. Obviously, in this case, like I mentioned, this isn't really a regression task, but we could use regression. But we'll see later that it doesn't get good accuracy. But because we're using regression, we only want one output, or at least in this case, we only want one output. And so we're going to set our output to be 1 because we only want one prediction out. And our activation, you guys will see there is no activation for this. Having no activation is the same thing as having activation equal to a linear activation. Linear activation is the same thing as having no activation. So all this last layer is going to do is multiply the weights of this layer by the previous output, the output of this layer, plus the bias, and it's going to have no activation. And again, this is the same thing as a linear activation. And so we're going to run this, and then we're going to do model.compile. This is a necessary step. We have to compile it, and we tell it what optimizer do we have to use. This is the gradient descent optimizer. Atom is kind of a common one. There's a couple of them. I'm just going to use Atom. This is just a commonly used one. But our loss is important. Remember, in our previous lecture, we talked about the different cases that you use. Right here. So in a regression scenario, we might use the mean squared error. We might use a mean absolute error. But in a classification test, we use a cross entropy. And there's different losses that you use in different scenarios. But this is important for our type of problem that we're doing. And so I'm just going to use mean squared error. And the way we specify that is tf.keras.losses.mean squared error. And then finally, we're going to set our metrics to be equal to our accuracy. Why we do this is because we want to see how accurate is our model. Is it predicting it accurately or not? Sometimes we don't care about accuracy. Maybe accuracy isn't a good metric. Maybe just our loss is a good metric. And so we won't use this accuracy. We'll use a different metric. But for right now, we care about our accuracy, and we're going to use the metric of accuracy. All right, any questions? All right.
Sorry, I think I actually do have one question here. So the activation function is linear on this very last layer. So that means that the final output is some real number, right? It doesn't have to be an integer.
Exactly.
And then our metrics are, you said not mean squared. Is that accuracy metric, is that like a categorical metric? Like if I get 5.001, but it's labeled 5, is it just like a 0 on my score?
Mm-hmm. So the way that comes up is while it's training, it compares the prediction to the actual prediction, which is your loss. Mm-hmm. But then it also sees what percentage is it getting it correct. And so let's say it got 5, let's say its prediction was a 5, and then the actual was a 5. Well, that's 1 correct out of maybe 50. And so that'll be a 1 out of 50 accuracy.
Okay. I guess what I'm interested in, and I'm sure we'll see as we go, is that if it's linear, like I'd expect I might get like 5.00001 instead of 5, and then the accuracy metric will mark that as incorrect, right?
Yeah.
Okay.
Actually, I'm not 100% sure about the regression, but I believe it's just trying to see how close to the possibility is it getting.
Okay.
Yeah. And so next, what we're going once we compile our model, we need to specify two variables. And we didn't talk about this in the last lecture, but this is our training step. When we do model.fit, this is the actual thing. This is all the steps are leading to this. This is what actually trains our model. And so we input our X train, this is our data, and our Y train, this is our labeled data. We also specify the batch size and our epochs. I'm gonna first talk about epochs. What exactly are epochs? So if you guys remember from our last lecture, we talked about gradient descent, and we had this step. Let me present this. There was this step in our gradient descent algorithm, which was loop until convergence. In practice, we don't know when it's going to converge. The way we do that is by specifying the epochs. But again, the epochs, it's sort of like a guess. The more epochs we have, the more iterations we have. So if we have 5 epochs, that means it's going through our data, our entire data set 5 times. And the more we have, if our model isn't complex enough, it might overfit. If our model is too complex, maybe we set it too low and it might underfit. And so this comes up by just experimenting, by just trying different values. And so for this case, I'm just going to set it to 5, but in the task given to you, you just have to experiment and see which epochs give you a better evaluation accuracy. So finally, this batch size. What's this batch size? People found out that this is one technique again, that every time you do the calculation of the layer, so we multiply the inputs by the weights plus the bias. Well, in our formula, it's kind of specified that we're only multiplying one input times the bias, times the weights plus the bias. But that actually doesn't get as good accuracy if you multiply more. So if you take, in this case, we have 64, a batch size of 64. What this is doing is taking 64 images and multiplying those 64 images by the weights plus the bias. And this has been found to actually increase the accuracy. And this again depends on the number of batch sizes depends on your specific task, and it's determined through experimentation. It doesn't matter usually too much. And for this case, I'm just going to set it to 64. And so this is our actual training step. And when we run this, this is where our model is going to apply gradient descent and when we're actually going to learn. And so we run this and we can see it's going through our data and it's printing out our loss. This is our loss based on the loss that we specified, our mean squared error. And it also prints out our accuracy because we specified we wanted to print out our accuracy. As you guys can see, our loss is fairly high. It starts at 2% or at 2, and then it keeps going down. That's good. When we know that our loss is going down, that means it's learning something. But when we look at our accuracy, we can see our accuracy is at 16%. That's not really good. It is improving, so it's going to 20%. But again, that's not good. It hasn't learned well enough. And even though the accuracy is increasing and the loss is decreasing, that means that the task that we gave it of a regression task, it's not good for this. A regression isn't good for this type of task. And so if you guys were given a task and you guys couldn't tell, is it a classification, is it a regression, try both of them and you'll see that, well, you don't get that good of an accuracy. And again, the reason for that is just getting a loss of 0.6 is bad because maybe the actual is 5. For example, the drawn image is a 5, but your loss is getting a 0.6. So it might be predicting a 4 because the 5 minus the 4 is 1, which is kind of close to the 0.6. And so it's getting it way off. So even if we have a low loss, our accuracy is low because it's not getting what we want it to get. And so when we actually go and evaluate it on our test data set, remember, because there's really no way, maybe our model is overfitting or underfitting, and we want to actually evaluate on data that it's never seen before. And so this X test data, this is, again, handwritten digits that it's never seen before, though, in the training step. And so we evaluate this, and we see this is the loss. We had a loss of 0.75 and accuracy of 20%. Again, this is not that good. And if you guys can notice, this loss is actually higher than the training loss. This means that we kind of overfitted. It doesn't matter too much though, because we're still getting a bad accuracy. So we overfitted, underfitted, it doesn't matter because a regression, the way we built our model for regression, it's not meant for this task. And so now let's actually go into classification. Let's actually do the technique that's meant for this task. All right, so this is another technique that we have to use because it's a classification task. We have 10 classes from 0 to 9. This 0 is the image drawn of 0, and this 9 is an image of drawn of 9. Well, in order for it to be a classification task, we want it to be the probability of it being a 0. What's the probability that our image is a 0? What's the probability of our image being a 1? And so on, all the way to 9. Well, for that, we need an array of 10 elements. And so what we do is we use a technique called one-hot encoding. And what this does is it encodes our input into an array of all possible classes. And so, for example, let's say our image is a 0. So in our regression task, the labeled data set would be this 0. But for our classification task, we one-hot encode this, and it becomes a 1V array. Now, what we do is, this is a 0. This is our first class. So the first class is going to be, we want this to be a 1. In our neural network, this is going to be the probability of it being a 1. And so obviously, because our labeled data set is a 0 for that specific image, we want the probability that it's at position 0 to be a 1. And so same with everything else. We want everything else to be as close to the probability of 0 as possible. And so this is what we want our model to learn. So again, if our image is a 1, we want it to be the probability of 0 to be as close to 0 as possible. We want it to be the probability of it being a 1 as close to 1 or at 100% as possible. And the probability of it being an 8, and an 8 is again specified by index 8, as close to 0 as possible. And same with 9. 9, we want the index 9 to be as close to 100% as possible. And the way we do this is using TensorFlow. And we do tf.keras.utils.toCategorical. And the categorical is going to be our training label data set with the number of classes. We have 10 classes, right? We have from 0 to 9, which is going to be 10 classes. And this converts each class into this encoded array. And so let's see what that looks like. If you guys remember, we print out the shape of our train. If you guys remember, our Y train used to be a shape of 60,000 to 1. So it was just 60,000 integers, or 60,000 of just some one integer. Now we have 60,000 of 10. So it became a 2D array. And this is what we want, right? Because now when we print out our first train, we get this encoded array. And this encoded array, if we look at it, we have, this is going to be 0, this is going to be 1, 2, 3, 4, and 5. So for this training image, the image should be a 5. And we can tell that by the index it is of the encoded array. And so now we're going to create our model for our classification task. And so what we do is model.sequential and then model.add. I'm going to use the same neurons just to compare it between the different types of tasks with the same 64 neurons with a ReLU activation, another layer of 32 neurons with ReLU. This is what's different though. Instead of having one output, we have 10 outputs. Why do we have 10 outputs? Because we have 10 classes. We want to have 10 outputs. Each output is going to represent the probability that it is that specific class. And so we're going to have 10 different probabilities. And now this is also different. We're using an activation of softmax. Softmax is if you look at the graph of softmax, it's a probabilistic formula, which means that it's gonna give a probability distribution from 0 to 1. And this is perfect for our task because we want the probability of it being from a 0 to a 1. And you can also use sigmoid for this. Sigmoid is also a probability distribution, but for this case, I'm just gonna use softmax. Again, I really encourage you guys to, after, mess around with this, like create a copy of this. I'll send a link in the Discord and just mess around. Mess around with the number of neurons, mess around with the activations, the number of layers that you have, add more, subtract them, and see what you get. Yeah, go ahead.
So this new, after the training, this model is going to output an array of size 10 with values between 0 and 1, and that's we're supposed to interpret that as the probability that the handwritten digit is 1 or 2 or 3.
Exactly.
Okay.
Yeah, like it's gonna output 10 elements, an array of 10 elements. If the probability, let's say the maximum probability is at index 0, then we know that it's predicting 0 because that's how we encoded using one-hot encoding, that's how we encoded our data. And so next we're gonna compile our model. I'm gonna use the same optimizer just to compare it using the item optimizer. And then this is also what's different because we have to use a different loss. And I'm gonna use a categorical cross entropy. This is common for categorical data or classification tasks. And if you just know that if you have only 2 outputs, you would use a binary cross entropy. But for this case, because we have 10 different outputs, we're going to use a categorical cross entropy. And our metrics is going to be our accuracy as well. So this is going to print out what accuracy we get. For comparison, and we compile this right now. For comparison's sake, I'm going to use the same epochs with the same batch size. And we do the same model.fit. The fit is going to be the X train. And this is our same data that we used in our regression task. Our Y train is different. Our Y train is our one-hot encoded data. It's instead of being just one integer, it's now one array. And so now let's actually run this. Well, all right, for some reason, I believe, let me see if I ran this. Okay. I believe I did not run that. Okay. There, no. Okay, I think because Colab, let me reset Colab. Because Colab remembers data from previous cells, so let me actually restart this runtime. Sorry about that. All right, so I actually have to import everything again. Actually, I'll just run everything now. Run all. And this is actually this is a good example because this is one of the most common errors that you'll get. It's of a shape error, which means that some of your inputs might be off, and that's probably one of the most common. That's why I try to emphasize the different shapes. And so yeah, that was the problem. So as you can see, we're actually running our model now, and we get a loss of starting off at 0.34. That goes down to 0.15, to 0.09, and 0.07. That's really low. And that's a good indicator that our model is learning because it's decreasing. Now when we look at our accuracy, it starts at a 90% accuracy, goes to 95, 96, and now it's at a 97 accuracy. That's pretty good. This means that the data that we give it is going to predict 97% correctly. But we can't just settle with this because we have to evaluate our model. We have to see, did it overfit? Maybe it's getting 100%, but it overfitted. So we tested on data that's never seen before. And when we run this, we see that our loss is really low and our accuracy is at 97%. So we can kind of conclude that our model didn't overfit, it didn't underfit, and that this is a pretty decent model. We got 97% accuracy. And so let's actually use this to predict things. So I'm gonna let's choose some random data points in our X test. So I'm just gonna choose the 50th image. And just to graph it, I reshape it back to 28 by 28. And this should be, so we print out our labeled data set. And remember, this is our one hot encoded data. And so this is supposed to be not a 0, not a 1, not a 2, not a 3, not a 4, not a 5, but a 6. And this is our image. And so let's actually let's actually use this to predict. And so we're going to set our prediction equal to model.predict. This is the function that we call. And we're going to predict our 50th image, but we first want to reshape that image to a 1 by 784. Again, TensorFlow is a little weird with this, but you do need, because before it's just a 1D array, because that's what we specified, right? Actually in our model, it's expecting a 2-dimensional array of 784 by 1. So we just have to reshape it to be of that size. And so when we actually run this is the prediction that we get. And if you look at this output, this is that prediction. If we count the number of, so let's actually count the shape of that prediction. It's a 1 by 10. This, ignore the 1, but this 10, remember, this is exactly what we want. This is the number of outputs in our last layer. And so we get 10 total outputs. And this is our probability distribution. This is the probability that we get a 0, or that our image is a 0. This is the probability that our image is a 1, and so on. So now what we do is we want to see what's the maximum prediction, what's the maximum probability, what does it think that this image actually is? And so we use NumPy, we do np.max of our prediction of this array. What's the maximum of this array? And we see that we get a 99%. That means that this is 99% accurate, that its prediction is what it thinks it is. And so now we want to print the position that prediction is in. What position is, because we care about the position. Depending on the position is what our image should be. And so we do np.argmax. This gets the position that our prediction is in, our maximum prediction. And we see that it's at a 6. And this is exactly what we wanted, right? It predicted this image correctly. And this is our model. We can see that we have a pretty good model. And if you want to, and this is basically what machine learning is. You train a model on data, and then you send it to some API or some website or some on an Android app or iOS app. And this is exactly what Apple's Siri and Google's uh, Assistant do. They train it on their system, and then they save that model and put it on your device. And every time it does predictions based on that trained model. Because it's predicting this data it's never seen before. But still, it's a good model and it predicts it correctly. And yeah, that's pretty much what machine learning is, using data to predict things without specifying, without programming. And we can see it had pretty good accuracy. And we'll talk about how to improve this accuracy. We can actually get better than 97%, but we'll talk about that in next lectures. So yeah, that's pretty much it. You guys have any questions?
I feel pretty good with this. That was good. This document's really good too. Did you make this document?
Yeah,
Yeah, the document's really good.
thank you. I'll share it in the Discord so you can mess around with it.
Okay.
Yeah. All right, I'll stick around if you guys have any questions. Thank you for coming. We'll have our next lecture in the next, not next Friday, but the next Friday, and we'll be talking about a different type of neural network called the RNN. And this is going to be useful for predicting time series. And we'll talk about why we even want that and why we need that. So thank you everyone for coming. And yeah, thank you.
Thanks, Monty.